adimensionalization. Okay, so let's do this, huh? So let's try together scaling and adimensionalization. Okay, so now we did talk before about finding a characteristic time in a system and stuff like that. Now the purpose of this is, given a model which is of a physical phenomenon, it has dimensions, is to get rid of the dimensions. Now in this process, the scaling would appear naturally in a way, okay? But more to the point, sometimes the number of parameters in the model will just be reduced to a smaller number that is the essential one that we need, or they just sometimes disappear. So the first example that I want to show you is the KdV equation, okay, which is the Korteweg, de Vries equation. Now I'm gonna put a link on YouTube on what this equation is about. It's a PDE describing a shallow water solitary wave. So I invite you to see that. So that describe, okay, a PDE that describes the shallow water solitary wave, okay, evolution in time, okay, and space. So it's basically about having a long channel, okay, let's call it, okay, I'm gonna take this and make it nice. There you go, here is X, okay. Okay, let's do it again. Okay, with the mean depth. So here it's gonna have its own mean depth. Okay, and then on top of it, right, is this wave that travels. Okay, so it's here now, and then later is the same wave, might be here, but I don't want to fill in the picture with all kind of stuff. I really hope you're gonna see the video, okay, with this experiment. Okay, so H is the mean water depth. Okay, that's one of a parameter. And now what really want is the unknown in this business. So if this is an X, let's say, okay, so here is this height right above of the wave as it travels above the level zero of the water, if you want, right, you know, the surface of the water. So here is this unknown that we're going to call it U of X and T. Okay, so there we go, X and T. So U of X and T. Okay, so let's actually, so we're going to have a change of variable. So let's put first the capital letter. U of X and T in capital letters, okay, is basically the elevation, okay, of the water, right, at position X at time T, okay. So this is the X, right? The X-axis if you want. So here, you know, we have a position X, okay. So X-axis. All right. Okay, now it was done, you know, from experiments, from certain assumptions in fluid equations of motion, we end up with the following equation of motion. So this shallow water wave, you know, its evolution in time is governed by the following PDE: du dt plus root of gh du dx plus 3/2 root of g over h u times du dx plus h squared over 6 root of gh, the third derivative of u with respect to x at 3 equals 0. Okay, so as you can see, this is quite a PDE, isn't it? Now, what are the parameters in this problem? We have, you know, parameters. Okay, we have h, the mean water depth, and g, the gravitational acceleration, right? So this is the gravitational acceleration, right? And now we have units for these guys. So the units for h is obviously is length, and the unit for acceleration is meter per second squared, right? So it would be length time at -2. All right, so this is quite a PDE, right? It's a non-linear, PDE. It's called the KdV equation, or Korteweg de Vries, by the time the guys who invented it. Now, you know, having these parameters in the problem, right? Not only that, you know, it's okay, we want to solve the problem. We always want to solve these PDEs, right? But, you know, as it's written like this, we could think that, oh, you know, as h is bigger or smaller, right, the mean depths could be larger or smaller, then we would have different solutions, or, you know, it's like the dependency of the evolution with respect to the parameters. However, if we're gonna apply on this equation the process of adimensionalization, so right now in this written down PDE, we assume that the dimensions that u, right, so this function that is the elevation, right, above the surface level of the water, right, which is the unknown, the units for u, right, will be length. So, you know, its elevation is the height over, right? So what we will do right now, we will get rid of the dimensions in the problem, okay? By introducing, if you want, in analogy with what we did with the characteristic time, we are introducing a characteristic time, and we're introducing a characteristic length, right? Of some sort, but I won't specify them. I would order what we're gonna do. We're gonna just say, look, you know, right now, t, right? For instance, this t has units of time, right? Because it's time. U has units of length. I would like to write the PD with no units involved. So, you know, it's nothing like that. So what one does in this case, here I'm going to write again the PD just to have it. Here it is. Okay. I'm going to write it smaller now so it fits on one line. Okay. Root of g over h u times du dx plus h squared over 6 root of gh, the third derivative of u with respect to x is 0, right? So the question is, what is this? And all these guys have units, right? So the units for x is length, the units for t is time, the units for u is again length, okay? And then these guys, right, as we had it, So x has units of length, t has units of time, u again length because it's the elevation, and I could write for the other guys again what they were, g and h, right? So now how do we do this process of adimensionalization? So I'm going to write here adimensionalization, right? Process if you want. So what this means basically getting rid of dimensions. Okay, so how do we do this? It's like introducing, as I said, the characteristic time length and so forth. So for this problem, we're gonna do the following. We're gonna introduce a little x to be capital X over h. So in other words, we're introducing as characteristic length h, the mean depth of the channel. We're gonna introduce an adimensional time that will be given by this quantity, okay? Okay, t. So in other words, if you want to recognize it, so t would be little t, the time, capital T, which has dimensions, over this thing. So it would be over 6 root of h over g, right? So it's the inverse of that thing, right? So then when I'm writing it, so in other words, this guy will be like the characteristic time from before, right? From the previous lecture. And finally, u, okay? So the little u will be the new adimensional elevation, if you want, that is capital U over h again. So basically, these things are nothing else but changes of variables. So we're going to do change of variables. So how to achieve this equation with no dimensions is by a change of variables, in which, you know, we basically divide each of the physical variables that are showing up in the problem to a characteristic scale in that particular variable, right? So for length, we're going to have a characteristic length. For time, we're going to have a characteristic time, and so forth. Now, when we're doing this, what is happening, we're going to start substituting into the equation. So to write this equation in terms of this new variable. So for example, okay, so for example, for instance, we had du dt, right? So what would be this in the new variable? So this would be d of little, right, of capital U. What is u in terms of the new variable? Oh, u would be h little u, right? So it would be d of h little u with respect to now dt. What is dt? Oh, dt actually should be, by the chain rule, db dt, and then d little t, a d capital T, right? So now we're gonna see what is this. So remember, so from t equals 1 over 6 root of g over h capital T, we deduce immediately that dt would be, right, dt at dt, at the capital T. So this is, you know, basically a function of capital T. So this is the derivative of whatever is on the right-hand side. So t is going away. So we just stay with that. All right, so now we know what is this. Here is h is a constant, so it pops out. So we end up with du dt equals h, right, d little u dt times that constant, okay? So that is du dt will be, so this guy comes in front here, and after some algebra will be a 6 root of gh d little u dt. Yeah. So we do this with all terms, right? and then we substitute, right? So this capital du dt, right, which was here, we're going to substitute it with this quantity, and then the rest is the same, du dx, nice, and so forth. So once we do this, so this is a calculation that I'll let you complete. Okay, so we do all this substitution, and remember, this is nothing else but substitution with the chain rule, right? We end up with an equation, and then, which I don't have and I don't want to do, however, and then plus an additional substitution, and okay, at the end of it, new substitution or new change of variable. Okay, new change of variable was by introducing, let's say, let's say x tilde, okay, equals little x minus t. So it's a shift, okay? So if we do this, then we're gonna end up, so in this case, having, you know, u of little x and t is identified with a little u of x tilde and t. So essentially is about changes of variables. Okay, let's see if I did it right. So this is little x, that's correct. After all this substitution and change of variables, we're gonna end up with the following equation. So blah, blah, blah. And then we end up with something that looks like this. Little du dt plus 6u u x tilde. Okay. Okay, little x tilde. Now I can do it calligraphic or not, you'll see. You'll know which one it is, okay? Plus the third derivative of little u with respect to x tilde 3 equals 0, right? So I'll let you try this. Please do it, okay? It's a calculation. And now this is the transform, right? So this thing is the adimensional form, if you want, of the KdV equation. Whereas what we started with, compare this with the dimensional form. So here I'm going to write again the dimensional formulation of the KdV equation. And I'm doing this on purpose, one under the other, so you guys can see the advantages of these two things. So this, let's say in red, okay, so the equation in red is the dimensional formulation of the KdV equation, whereas this one in blue here, right, is the adimensional, let's say, formulation, to be consistent, of the KdV equation. So you can see that there is quite a difference, right? So in this one, in the dimensional formulation, right, we have two parameters. We have G and H parameters, right? And we don't know how the dynamics, if yes, you know, how it will be affected by varying these parameters, if for larger h or smaller h, you know, if the dynamics will change. Whereas it's clear that in the adimensional formulation of the KdV equation, there are no more parameters actually. Magically, they disappeared. Then so they disappeared just because, you know, the dynamics of this you know, the evolution of this equation is independent of the parameters, right? So they affect, you know, in this, right, this coefficient there, 6 and the rest, right? So this is the first example I wanted to show you, okay? And it's not worked, you know, so I'll let you complete the works, okay? Now I have another example which is fully worked, okay? So we're gonna discuss it together, yeah? I mean, I'll present it to you. So let me flip a page, and this is about a nonlinear diffusion equation. So it's the so-called Fisher equation, okay, which is a nonlinear diffusion equation. Okay, there you go. So its form, it's actually models the concentration of a chemical in, I don't know, chemistry experiment. So it has the following form, right? So is a PDE. So the question is, find that function phi that depends on time, on position and time, okay? And this is nothing else but the concentration of a substance. In chemistry experiment or something. Okay, so I'm just taking the equation, and now this phi is good to know is measured in unit per volume. Okay, so it will be Ln minus 3, by the way, okay, as units. But what's the equation, right? Is the following, is diffusion, right? So it's like the heat equation, it starts like that. It has a diffusion coefficient D. Okay, here is the second derivative term. And now comes the nonlinearity. Otherwise, this would be just a linear equation, right? So here is minus lambda phi times phi minus gamma. Okay, so these are some parameters that are given. So D is the diffusion coefficient, and its units, I think we discussed it before, is L2 T at minus 1. So it's area per time. And then we have lambda and gamma. There are some parameters in the problem, okay? And their units, okay? So lambda units, okay, with right, so actually we could deduce it, isn't it? Okay, so let's deduce it together. Okay, so here, what would be the lambda units, okay? So here, d phi or dt, so whatever lambda units is, or actually, let's write again the equation, okay? So this is a side thing, okay? Like how to deduce the units in a model, right? If we know some of the units, what are the rest? We just have to match them. So this is, I'm just rewriting the equation, right? So this is a phi squared plus, well, I don't have to. I don't have to. Okay. So let's think together, right? So d phi dt, the units of d phi dt will be the units of phi over time, right? So the units of phi was L at minus 3, and then over time. So this is L at minus 3, T at minus 1. And this has to coincide with the units of this term, right? And then multiply by the units of this bracket, which are the units of phi. So this guy will have the units of phi, okay, which are ln minus 3. And then this thing, right, whatever this thing is, well, we know what phi is again, so this, the units of phi is for phi. So this has to coincide here, let's just say it like this, with the units of lambda, which we're looking for, but then with the units of phi, which is, so for this guy would be L at minus 3, and then another L at minus 3 from the bracket, right? So now it's clear. Okay, so what would be the units for lambda? Okay, L at minus 3 is going away. So it would be L at 3, T at minus 1. Yeah, and we deduced it. And now the units of gamma, you see that one is the easiest because gamma is in a bracket with phi, so it cannot be at the units. So phi, it has its own units, and gamma better have the same units of phi because otherwise you cannot add them. So if phi is 1 over meter cube, gamma cannot be meter per second because you cannot add meter cube, 1 over meter cube with meter per second squared. So there you go, okay? So this guy definitely has the units of phi because it cannot be otherwise. So is L at minus 3. So we have the units established, right? Okay. So we had this discussion. So there's the PDE. Now the PDE comes together with boundary conditions. Okay, so I'm going to flip the page. And I'm going to rewrite the PDE. Okay. And now comes, so, this guys, these parameters, lambda, d, their parameters. Okay. So now let's see the boundary conditions and the initial conditions. So first we have initial some initial conditions, right? So they're given. Okay, where are they? Where are my initial conditions? There you go. So we have a phi at x in 0, that's an initial condition, equals, well, some initial condition, right? So let's say it's a phi naught, okay? Why not? And then I'm going to just say that this is 5 pi x over L. Okay. So I have a comment about this and I'll do it in a second. So this is the initial condition. And then we have the boundary conditions given as of this form. Okay, let's say 0. So this equation is set up for x in between a and b. Okay, so that's why we have that AB at the edges here. So it's here, right? And let's say t is positive. Okay, that's the time. Now, as an observation about the initial condition, okay? So I was saying I'll have an observation about the initial condition. So on purpose, I'm choosing this, okay? So phi naught, so I'm referring again at dimensions. Phi naught will have the dimensions of phi. So these guys go hand in hand. So it's again L at minus 3. But then I wrote, a sine of phi pi, right? And x over L, okay? So sine of something has no dimensions. So sine of x is an adimensional quantity. But if it's adimensional, right? So in particular, so let's say sine of not x, let's put a different letter, like sine of an alpha or something, right? Where alpha is an angle. Okay. And again, we're going to say that this alpha, has no dimension, is adimensional. It has to be adimensional. Mhm. So why am I saying this? Is because when we're writing as a function of x, and in this problem, right, remember x is a length. So if I would write sine of x with x having the dimension of a length, this is so wrong, because I cannot have, so this is something that is a contradiction I'm making, that scissors of mine, right? Because, okay, we cannot have sine, there is no sine of 2 meters, let's say, okay? There is a sine of 2, but not 2 meters. So this is okay, but not something with a dimension in it. There is no sine of 5 meters per second squared. There is no sine of 10 meters squared. There is no sine of 10 meters. So that's why when we're writing this initial condition here, right, it is a function of x, but then it has to be adimensionally given, right? It has to have an adimensional form, because otherwise it's wrong, right? So here is x over L. So overall, so x, when we write sine of x over L, right, we have the dimensions of x coincide with the dimension of L, and this is dimension of length, right? Where L, we understand that L is the length of this interval. So this is the problem in its beauty, okay? So what we're gonna do now, let's write it nicely, okay? So this is the Fisher equation with dimensions. What we're gonna do, keep doing this, huh? We're gonna adimensionalize it. And in this process, as we will see, okay, some of these parameters will disappear. So we have 3 parameters, or, you know, they can be, we can manufacture, you know, finding these time scales and whatever we're going to use, you know, and the length scales in order to adimensionalize this problem. We're going to be able to choose them in such a way that little miracles will happen, and the number of parameters will go down, and the boundary conditions will look nicer. You know, we kind of build a model that is, you know, catches all the generalities in some, you know, clear one equation, and, you know, with the conditions that are associated, yeah? Okay, so let's see how we do this, right? So first thing is first, here I'm gonna write again the equation, of course. Okay, equals d 2 phi and x2, because that's the one I'm gonna do first. Phi minus lambda, no, lambda. All right, so we're gonna introduce x. So this would be the adimensional length, okay? Which doesn't make sense to say it, but that's what it is. Okay, so x over alpha, okay? Alpha is not known, but what we know about alpha is that it has dimension of length. So this ratio here has no dimensions. Then we're gonna introduce an adimensional time. And then again, this tau has dimension of time, okay? And it's not the same t as, okay, so maybe I should make it, it's dimension of, okay? And then phi, little phi, will be phi over c. With little c, again, we'll have the dimensions of phi, in which case is L at minus 3, yeah? Okay, L at minus 3. All right, so we don't know what alpha, tau, and c are. We might choose them at the end. We will choose them at the end, actually, so we can simplify our model as much as possible. But for now, right, so alpha, tau, and c. So this will be, so this characteristic, because that's what they are, characteristic variables, okay, will be chosen later, and we'll choose them in such a way that, well, as I said, we'll simplify the model. So now basically what we have here, we have a change of variables, change of variables. And again, we have to deal with the chain rule and stuff like that, right? So basically we're going, if you want, from x, t, and phi, we're going to some new variables, which are little x, little t, except capital phi, of course, okay, and little phi, with via the formulas above, right? So we know, for instance, that x, right, little x, so I could write here something like x over alpha, just to be kind of complete in my exposition here. But okay, what we will use for sure is that, okay, x is alpha little x, we're going to use them in our computations. T is tau t, and phi is little c and little phi. Okay, so now we start with the computation. So what is d phi a dt in terms of the new variables? This would be a d little c phi. Instead of dt, we have to do db dt, dt at dt, right, like before. So this is like in the previous example, if I had dt, and then here dt at dt is 1 over tau, okay? So basically we have d phi at dt to be little c over tau, little phi, little t. So that would be the left-hand side in the equation. Now we have to do the next term. So d phi at dx, and then again at dx. So this will be d little c phi at d little x, and then d little x at d capital X. So this is c d phi at dx times d little x, okay, at d capital X is 1 over alpha. So it will be little c over alpha d phi dx, right? So that's with that. And now if we do the second one, so this is d dx of little c over alpha, well, okay, has no jump, huh? D phi dx. So this is d dx of c over alpha d phi dx, d little x. Right? So this is now c over alpha d d little x of d phi little x, and then d little x at d capital X. Oops, it doesn't have to be round. Okay, and then again, this is 1 over alpha. So overall, we're going to get that we have a c. We end up with c over alpha squared d2 phi a d little x2. So there you go. So we can conclude. So d2 phi a d capital X is c over alpha squared d2 phi dx2. So there you go, there's that. And we have the other one, right? Here. So we're gonna go with this 2 into the top equation, and we're gonna substitute, right? So what do we get? We get c over tau d phi dt equals d times c over alpha squared d2 phi d little x2 minus, okay, so remember phi It's here, right? So phi is c little phi. So we have here minus c little phi. So first let's put the lambda. Lambda c little phi times c little phi minus gamma. Okay, so now if we are getting rid of c, which is non-zero, so all this thing in modeling is right, they're non-zero, it cannot scale by zero. Okay? We end up with d phi dt equals tau d, okay, let's write it nicer. So it will be a d tau over alpha squared d2 phi a dx2 minus lambda tau phi, good, c phi minus gamma. Alrighty. Okay, so that's what is going on to the equation after we substituted with the new non-dimensional or adimensional quantities. Now we have to see what happens in the boundary conditions, right? So what we have to keep in mind is that phi in capital X and T is nothing else but C in little x and t. And then the connection in between capital X and little x is, as it says on this page, where is it? It's up there, right? So this, this, and this for the three of them. So this would be alpha x, and then for t, this is tau t. So now we had the boundary condition that phi in x and t, boundary condition, right? So phi in A and T equals phi in B and T equals 0. But what would be this one? This is C phi in, so A, right? So here is A equals alpha. And if you want the new A that is adimensional, but basically here I'm going to just put A over alpha, and then T, little t, is T over tau. Okay, and then this was given 0, and then we had the other one at the other end. This is C phi in B over alpha, because B is like the X, right? So maybe I should have written this. Yeah, just bear with me, right? And then the other one is T is tau T, or right, little t. It depends what we need, right? So now I think it's clear that little a becomes, right? So this would be like the capital X, and then the little x would be a over, right? Divided. So this capital X is a, and then we divide by alpha. So this is again 0. So in other words, what we get, okay, we get that phi in a over alpha, and then little t, okay, equals phi in b over alpha, and then little t equals 0. So that's the boundary condition. And now with respect to initial condition, right? So that one was phi was phi of x, and 0 was given as a phi naught sine of, what did I say, phi pi or something, sine of phi pi x over L, right? But x, okay, x over L, just stay x over L. Okay. All right. So what this one becomes C little phi in okay, in x over alpha, which is little x, and 0 would be phi naught. This is p and the phi 0 if you want, and then sine of phi pi, and this is adimensional, so okay, we don't have to do anything to it. So in other words, we end up with phi in little x and 0 equals c phi naught sine in phi pi, if you want, alpha little x over L. All right, so this is the initial condition. So maybe I should, okay, no, that's blue because I used blue for the equation. So the system after the adimensionalization process ends up to be this. And you know my habit, I'm going to turn the page and write it again to see it. So after, right, after the change of variable that was x is alpha little x, t is tau t, and phi is little c little phi, okay? Our model becomes the following. So where is it? It's d little phi dt equals d tau over alpha squared d2 phi d little x2 minus lambda c, lambda tau c, that's exactly how we go there, okay? Little phi, phi minus gamma over c, right, because I pulled the c factor out here. So here I'm gonna pull this one out, okay? And that's why it's in front there, and now it's gamma over c, okay? And then together with an initial condition. Okay, so this is c phi naught sine of phi pi, what did we say here? Alpha x over L, okay? And so this is the initial condition, and we had boundary conditions here, a over alpha 0 equals phi b over alpha 0 equals 0. So this is the right. And while this model is adimensionalized, we have now the freedom to choose alpha, tau, and c. You know, to choose them in such a way that we can simplify, you know, this PD as much as possible, if possible, and the boundary conditions, right? So we still have to make a choice, or still have the freedom. There we go. That's a nice way to say it. The freedom to choose alpha, tau, and c, right? And how we're going to choose them is, I repeat, to simplify this stuff as much as possible. So for instance, for example, okay, the easiest way to do it, I mean, one way, there is no perfect way if you want, you know, but our interest is to, again, to take a model with many parameters and kind of reduce the parameters to some numbers, you know, but, you know, basically, if you have less parameters, you have less discussion to make, you know, less analysis, right? So, you know, it's good, right, to have less parameters in the problem. It's less complex, the problem. So for example, okay, we can choose, okay, choose alpha, right, such that to be L, okay? So L was right, the length of the interval where we are doing this analysis, A to B, right? So we can choose alpha to be L, and then let's see what is going on here. The boundary conditions become phi in A over L 0 equals phi in B over L and 0 equals 0. Okay, so in this way we're introducing the characteristic lengths to be actually the lengths of the interval where we are solving the PD. That makes sense. Okay, this doesn't do much for us. However, we can also then also is this choice. So there's the boundary condition. The initial condition becomes sine of phi pi, and alpha over L would be 1 sine of x, right? So sine of phi pi x. Okay, now it becomes a function of x, pure and simple. Okay, we still can choose tau and which one it is, and C, right? Okay, so I'm going to choose one. One S or two, one over two. So choose tau such that d tau over alpha squared is 1. So i.e. d tau over, because we already chose alpha, L squared is 1. So in other words, tau will be L squared over D. Okay, so we have these choices already. Alpha is L and tau is this, okay? And now what will come of this guy? And so we have that lambda tau C will become lambda L squared over D C. Okay, all right. So for now, what do we have? We have alpha L, tau was L squared over D, and our model is d phi dt with these choices, right? We have that the coefficient in front, okay, sorry, what is beta over alpha squared is 1. So this guy disappeared, so it's d to dx2 minus, and now all this stuff here, lambda tau c phi, because lambda becomes lambda L squared over D, L squared over D, C, and then phi minus gamma over C, right? So that's what the ODE now. But we still can choose now the C. So choose, how do you think I'm going to choose C? Huh? Maybe I can do all that guy. No, let's see, C. Okay, maybe I'm gonna choose C. Let's see what I chose in this story here that I had to be actually another final. I don't think I can do that. So right. So this thing as I'm going back, right? So I just substituted here as C is C little phi naught, but basically we don't know what little phi naught is, right? So it's okay. So phi is actually phi naught would be big phi over c. So what did I do here? This is not correct here. Let's correct it. So this would be a phi naught over c in front, right? So that's the little phi naught. Okay, I was wrong there. So then I can correct this stuff. Wrong there, and you didn't say anything. Okay, so phi naught over C. Good. Okay, I'm correcting everywhere. I'm not shooting this video again though. Phi naught over C. So we are here, right? So now I'm going to choose the C so that this guy becomes 1. Okay, so that's what I'll do. Choose the C. So, okay, so i.e. phi naught is actually little c. All right, so with this choice, what is happening? Our problem becomes the equation minus lambda and then this parameter. So instead of c, I'm going to put phi naught and the d, and then phi minus gamma over phi naught. Okay, because it's instead of c, instead of phi naught, instead of c, we have phi naught. Okay, and we have these are the boundary conditions first. And then the initial condition, which looks now like something that we studied in the PD course, sine of phi x. So now it looks like some PD that perhaps is a little bit more familiar. However, these things, right? So I can actually put all these guys together and they become one parameter. Okay, so here it is. Let's call all this stuff, let's call it epsilon. Okay, so it doesn't have to be small, it's just the name, epsilon. So then we end up with d phi dt equals d2 phi dx2 minus epsilon phi minus gamma over phi naught. Okay, this is another letter, could be just another letter. Okay, let's make it a del. Okay, so I'm going to call this term to be del. Okay, just to make a point that we have less parameters in this problem. So we started with uh, 3 parameters. So let's look back for a second before concluding. So we started with this problem in which we had 3 parameters. Okay, where did I put it together? Right. So we have as parameters these d, lambda, and gamma, right? And it was a dimensional equation with dimensions in it. And then what we did by the process of adimensionalization, right? Getting rid of dimensions and looking for the right time scales, characteristic scales, because it's time and spatial, scales, choosing them at the end. So we did this changes of variables that basically adimensionalize the equation and its initial and boundary conditions, okay? And after we did this process, which involved some change of variables, chain rule, right? Some thinking about the boundary and the initial conditions, right? So after we did this job, we chose these scales, right? So these are characteristic scales. So we are managed to choose them in such a way that really they simplify the PDE. We reduce the number of parameters from 3 to 2. So in this problem, it's just epsilon and delta. They're parameters. They're not more, right? Okay. So, you know, we reduce the number of parameters and the problem is adimensionalized, and it looks like something that we can actually put our hand on and do some PD theory on it, you know, as we learn in PD course. So I hope this video will help you. And as I said, on Monday, we're moving on to a different topic.